Alright, picking up where we left off, the last thing we were talking about was range, right? We were talking about the options there. Okay, there's a couple of other things that would be worth talking about here. I might get lazy and use this notation, or you might see it written this way before. Okay, this symbol right here means all real numbers. This is just instead of writing from negative infinity to infinity, we might use this bold R, so it kind of looks like this when I write it. Okay, the old writing symbol, if you were familiar with that. Okay, so a couple of things. Most of our functions have domains that are all real numbers. So the constant function here is the any linear function has that. X squared has that. Pretty much any polynomial function. So any power of x function has domain all real numbers. You only get a different domain when it has a pretty weird function, which we're actually going to talk about right now. Okay, so another notation might be this kind of weird backslash here. You might also see it like this, like a subtraction sign with it, minus, and this curly brace thing means the set of. Okay, so if we needed more than just 0 in here, you could just put a comma and put like 1, 2, if there's like more than ones that you're not allowed to have. So let's undo that, but I'm going to probably write it something like that. Okay. So examples of where this might occur are these weird functions right here where we've got asymptotes. Okay, so notice that if we try to plug in 0 here, it doesn't quite work. Same thing right here, you're getting really, really close to 0, but not ever touching it. And then this one is kind of an example of a hole in the graph. It's not at 0, but the domain is all real numbers except for 2. So we would write that as that R backslash brace 2. If that makes sense. Okay. All right. Kind of the last thing we're going to be able to talk about here are the intercepts. Okay, and this is going to be one of the most important thing we talk about when it comes to functions. Okay, because when starting from last year and going all the way up to calculus, when you want to optimize things, when you want to look at the minimum values, when you want to look at what is your revenue to profit cutoff place, that's where you're going to want to look at the zeros of your function. Okay, so I'm going to use these pretty interchangeably because they do mean the same thing. When I talk about x-intercepts, I'm talking about the roots when I say something algebraically. So for example, if I wanted to solve this guy, plus 9 is equal to 0, really I'm asking you to find the roots of function of 3x plus 9 equals y. Okay? Or if we're talking about the zeros of a function, the reason why it's called that is pretty boringly enough. It's where the x equals 0 on here. Okay, or I should say the y's are equal to 0 on here. So it would be like 1, 2, 3, 4, and this guy's 0 right here. I don't know what the function is, but this is the value that I cared about right here. Okay, so it's where the y value is 0, and then graphically speaking, it's where it intersects the x-axis. Okay, and you might have plenty of these. I'm going to look at the sine curve in a second, but the y-intercept, notice I said that is the location where the graph intersects the y-axis. So I want you to think about this. Why did I make the assumption there's only ever going to be one y-intercept? Bring that in for me tomorrow. See if you can figure that out. Okay. So let's look at these two functions right here and see if we can pick out. And this is going to be pretty much the extent of which we're going through stuff now. Let's see if we can find the x-intercepts. So the x-intercepts for this guy, now this one repeats over and over again. Okay, but it looks like we got one at 0, one at pi, one at 2 pi, one at negative pi, and one at negative 2 pi. Right, so there's a lot of them. So if I just asked for, let's say, 2 of them, I would say 0, 0 is 1, and let's say pi 0 is another. Okay, so this is where I want to stop and and specify something. Notice the notation I'm writing this. I write them as an ordered pair because those are the actual points. Now, in context, you have to realize that this looks exactly like all the points from pi to 0, like that notation that we looked at before. But it's going to be an ordered pair. So when we talk about points, that's what we care about. Also, you might see it as this. If we're talking about x-intercepts, we know for a fact that these are going to be when y equals 0. So sometimes you might see it as just written as x equals pi, x equals 2 pi, and so on. Okay, but either one of these is acceptable for me. It just depends on how they ask for it. So let's move over to this shape over here, this parabola. Let's find the x-intercepts. So it's where it touches the graph. So right here it's going to be 1, and right here it's going to be 3. Okay, so again, our x values when y is 0 is 1 and 3. And that's totally acceptable. Or if you want to write it as 1, 0, and 3, 0, that's totally cool too. Okay. Now let's look at the y-intercepts. And now, there's only one for this sine curve, and it's going to be right at 0, 0 again. So the intercepts here are y is equal to 0. For this one over here, it's y is equal to negative 3. Okay. Hopefully that's pretty clear. I think that's about all we're going to cover. Let's look. Yeah, okay, so let's go through one more thing. I want to talk about the extrema. Now, I didn't type this up, but I can kind of write it up now. Okay, the extrema is a fancy way of saying the max or min of a function. Okay. Now, sometimes you might see a couple of different things here. You might see the absolute extrema, or sometimes you might say the local extrema. Okay. Now, the reason why we want to look at both of these, the extrema, if we're talking about the max or the min of the function, we want to, again, these are very important for optimization techniques. And again, seeing what the domain and the range is, those are big helpful clues for both of those things. Okay. Now, the absolute extrema, when we say the absolute, we're talking about like on the entire graph, what is the highest value? Okay. So if we go back to the parabola here, okay, so draw this pretty poorly, but let's see here. Okay, so the parabola looked kind of like this. Okay, and no matter how you orient it, it's going to be kind of the same way. Okay, this one will have an absolute maximum. Okay, it will have the highest point right here. Okay, or if it's maybe flipped the other way, it'll have the lowest value at the place we will call the vertex. And we'll talk about this in the next couple of weeks because these quadratic parabolas are going to be our focus of study for most of the semester. Okay. Now let's look at the, if we look at the local extrema, though, the local extrema is going to be just in its neighborhood. Okay, so we talked about the sine curve a little bit. Okay, so sine curve looked like this, right? Okay. So notice that these have these hills and valleys here, and that's essentially what we're looking at for absolute max and min. Okay, this thing right here is going to be a local maximum. Okay, and why is it a local maximum? Because it's going to be, it's not the highest value on the graph, because this one is going to be tied with it. Okay, but in its little neighborhood here, it's going to be the largest value. And likewise, these guys down here are going to be the smallest ones in its little neighborhood. Okay. So that's essentially what we mean by extrema. The extrema are going to be the max or the min. Okay, so we can say that a function has a local maximum, it has an absolute minimum, it has an absolute max. But if I ask you, okay, what are the extrema? Can you point out the extrema to me? That's what I mean. Okay, we have about right around 10 minutes here, so we'll talk about periodicity and end behavior in class today. So that'll wrap up for this flipped classroom.